I've been working on machine learning for many years, and last 5 years I've been focusing on deep learning for conversational AI interface. So before ServiceNow, I started a conversational AI company, Passage AI, and so this is some of the lessons I learned building conversational AI interfaces in last 5 years. So let me start talking about what I mean by conversational AI interfaces. So we see now more than 300 million smart speakers from Alexa devices to Google Home, and they are growing very rapidly. And in fact, it's predicted to overtake number of tablets this year. And also, we have billions of users on messaging platforms like Facebook Messenger, WhatsApp, Microsoft Teams, Slack, and so on. And all these messaging platforms have been opened up for developing virtual agents, messaging bots, and any business can create a conversational interface on these messaging platforms. And we also see more and more devices with conversational interfaces like TV remotes, wearables, and so on. And it's great to see these conversational interfaces on these new devices, and you don't need to learn new interface for each device, and you can just converse with these devices. Uh, and I see conversational interfaces are future of computing interfaces where every computer is equipped with a conversational interface. It's already happening from Microsoft Cortana, Siri, Google Assistant, Alexa, and so on. Just a few years back, this is a screenshot from movie Her. Conversing with device seems like a science fiction, but it's a reality now. At the same time, when we see enterprise side, 80% of businesses want an automated conversational interface very soon, so that they can automate various parts of customer service and be available to their customer 24/7 rather than only during business hours. At the same time, more and more customers are getting used to bots or virtual agents, and they would prefer talking to bots to resolve their issue rather than waiting online or in the weekend, not able to reach out to customer service. So what does it take to build a conversational interface? So there are three components to build a conversational interface. The first one is the ability to define workflows and interactions. Uh, and I'll go a little bit more in detail of what I mean by ability to define interaction and workflows. The second part is natural language understanding, processing, and have a conversational AI capability. And the third is ability to converse with users in their medium of choosing, whether it is a voice medium or messaging medium, and adapt for voice or messaging mediums with native capabilities of that medium. So what are the building blocks for conversational interface experience? The first one is ability to define interaction. It could be a mind map of user interaction and ability to handle errors and disambiguate. The second building block is having a way to define workflow using tools like intents, API calls, decision tree, knowledge bases. And the third is ability to train conversational AI by providing definition of intent, utterances, and what kind of responses are expected. So some lessons developing conversational interaction design, make it personable instead of, let's say, just saying, hi, how can I help? Say, happy Friday, Pete. What can I do for you? Be available all the time, not just navigational, because in the middle of your navigational workflow, A user may ask to do something, and your virtual agent should be able to respond back. Ask for clarification and disambiguate in cases of ambiguity or many choices to narrow down choices, and never end conversation uh, at in the some point. And the ability to handle errors and not supported features gracefully. Here are some of the building blocks to build the workflows. Intent is one abstraction to define a use case that can capture meaning behind messages and curate responses. Have ability to define action fulfillment and workflows by making API calls or executing a particular workflow. So example of workflow could be, let's say, for customer service, for e-commerce, it could be order tracking workflow. Or in an enterprise environment, let's say somebody wants to reset their password, have the ability to get appropriate variables and parameters and execute a workflow to do certain tasks. Decision tree. So troubleshooting, like use cases, you want to walk down a certain path of troubleshooting and have a decision based on what user has responded so far. And finally, knowledge base for question answering. A lot of information is stored in knowledge bases, documents, and be able to extract, write, answer for a given question. So let me switch gear and talk about how advances in deep learning technologies are making conversational AI a reality. So first step in making a virtual agent intelligent is to understand what users are saying. This involves natural language understanding, such as extracting right pieces of information, entities, location, names, etc., and also understand meaning behind the messages through abstraction of intents. I gave a couple of examples, let's say order tracking in case of e-commerce, or reset password intent in case of enterprise. Those could be examples of various intents. Finally, need to understand what actions you users want to take and do appropriate action, like trying to get more information from users to execute certain action. So for example, in case of order tracking intent, you need order ID from the users and also have an ability to verify the user you're talking to. Similarly, for reset password, you may want to authenticate users and get some information back to execute that action further. Also, ability to respond back to users in natural language is important. And all this is feasible using some of the latest deep learning technologies. So here is 2-minute introduction to deep learning. In traditional machine learning, someone has to design features and engineer those features. And machine learning model optimize weights or come up with a combination function that combines those features to predict the outcome. On the other hand, deep learning stands, which normally stands for deep neural network. You have layers of neural network, deep neural networks, and they are good in understanding various levels of representations from the data. So you feed the training data and the outcome, and various layers understand various features and levels of representation for given input. For example, in this case, this is, let's say, a convolution deep neural network to identify face, a human face versus cat face. You have convolution layers, max pooling layers, combination of that, then dense layer and softmax to be able to understand various feature representation, whether it's like lines on the face and so on, and finally predict whether it is a human face or cat face. More recently, deep learning has been very successfully applied for various natural language processing tasks, whether it is language translation, question answering, speech recognition, and so on. And I'll briefly describe two important techniques. One is having a pre-trained language models for embedding, uh, uh, and second is adaptation and fine-tuning. So examples of pre-trained language models for embeddings include Word2Vec, that revolutionized the NLP world in 2012, 2013, Glow from Stanford, Elmo from Allen AI Institute, ULM-FIT, GPT from OpenAI, and BERT from Google. So these are some of the examples of pre-trained language models that are making a lot of impact in natural language processing world. And uh, I'll go into some of the techniques for adaptation and fine-tuning recurrent neural networks, and example of that is long short-term memory network, as well as transformer network with attention models are used for adaptation and fine-tuning for a particular NLP task. So let me briefly describe what I mean by pre-trained language models for embedding. So, uh, to give an example is Word2Vec that came out in 2012 from Google, and that has completely changed the world of NLP in last 8 years. In Word2Vec, you were embed words in a continuous vector space so that semantically similar words are mapped to nearby points. This enables very powerful analogy operations. So you can do things like king minus man plus woman is a vector representation of these words. The vector you get is very close to the word queen vector, and you can deduce such analogy from Word2Vec. Before Word2Vec came out, natural language processing, text processing used to suffer from curse of dimensionality. Uh, so, so in bag of word model, you normally have a dictionary of words and counts in text. You use that to represent each word. It's an easy feature generation technique for text processing, but it has a lot of limitations. For example, it's very hard to capture order of words, and it suffers from curse of dimensionality because since let's say you have used 50,000 dictionary for English, even similar words may map in far away data points, and very hard to capture similarity between words. So word embedding in some sense addresses this curse of dimensionality and eliminates those limitations from bag of word. And even with more recent techniques like BERT, Elmo, you are able to even contextually capture the meaning of word, and the, as well as map the words in a higher dimensional space, typically 200 to 500, and learn representation of words in this higher dimensional space, so that semantically similar words are mapped to similar space in vector space. And this enables very powerful analogy operations. For example, distance between word vector for France and word vector of Paris is similar to distance between word vector of Italy and word vector of Rome. And this helps in lot of text processing tasks. Let's say, for example, you want to find out, let's say, capital of each country, that kind of task. If you want to train with even a small training data, you can do a really good job for such task. And how do you train such word embedding? One way, simple way, for example, to train word embedding could be a train two-layer neural network to learn word representation by predicting next word from a phrase. And output of first layer in your two-layer neural network, you could use as a word embedding. In fact, GPT 123 use next word prediction as their training task for pre-trained language models. So there's a lot of recent advancement in embedding. So some of the examples are a couple of years back, Elmo came out from Allen Institute of AI that uses bidirectional LSTM network trained on a particular NLP task, for example, text classification, to generate contextual word embedding. So because of LSTM layers, so let's say the Broadway play premiered yesterday, the play would capture embedding would be closer to, let's say, theatrical play versus, let's say, a sentence like, I want to play soccer. It will be a different word vector because of the contextual representation. And you learn this contextual representation by combining the final output, the middle layer, and the initial layer output. BERT is another one that came out late 2018, and there has been a lot of variants of BERT that are very successful, and that uses something called transformer network with self-attention layer to capture importance of words. And in this, these are somewhat faster because each word can be processed in parallel, and you can get contextual word embedding using models like BERT. Also, there's sentence embedding not that are very useful in many different contexts, especially in search and similarity, where you encode the whole sentence contextually. And Google's universal sentence encoding is one of such example that also uses transformer network for pre-training. So let me talk about the other component of natural language processing task for adaptation and fine tuning for a particular task. And sequence learning models and transformer network are two examples of such adaptation and fine tuning where deep neural network has been very successfully applied. So let me talk about the first one, which is using sequence learning model, that a sequence to sequence model that came out about 4 years back from Google, and it has been successfully applied for Gmail Smart Reply that uses a form of recurrent neural network called a long short-term memory network. So in recurrent neural network, output of one module go into module of the same type. And this is good for capturing sequences like sequence of words, sequence of characters, sequence of spoken words, and things like that. And long short-term memory network is one example of recurrent neural network, which has one long-running cell state, and output is a combination of the long-running cell state, the previous cell output, and the current input. And this kind of combination helps in capturing the dependency between words in a text sequence or characters in the text sequence, and having the ability to forget long dependency helps in addressing some of the limitations of earlier recurrent neural network, like exploding gradient. Uh, so, so another form of deep neural network that has gained a lot of attention in last 3 years are transformer network. These are basically layers of attention layers and feed forward normalization. And there's an encoder layer and decoder layer, and multiple uh, layers of transformers can be put together. For example, BERT uses 24 layers of transformer encoder trained on next sentence prediction task with masking to pre-train a language model. GPT-3 that that is gaining a lot of attention recently, that uses 96 layers of transformer decoder trained on next word prediction task. And these pre-trained language models come out of the box trained using a lot of data. For example, GPT-3 uses terabytes of data, and it has 175 billion parameters, according to some estimates that it took $12 million to just pre-train the GPT-3 model. So these are trained on large amount of data, very large model, but they come out of the box with ability to do a lot of natural language processing tasks. And on top of that, you can fine tune them and to adapt to your particular NLP task. So some of the NLP tasks that makes conversational AI reality includes identifying intents, extracting named entities, filling up slots for, I mentioned order tracking example where order ID is important, sentiment analysis, knowledge base, semantic search, machine reading comprehension for question answering. All these different components of conversational AI is possible using some of these latest deep learning technologies like pre-trained language models and adaptation and fine-tuning. So how do you train these various models? You need to provide ways of saying the same thing in different ways, provide various label data for different tasks, from intent identification to entity extraction to question answering, and avoid enough training data to provide enough training data to avoid overfitting. And you can divide the training phase where there's more powerful machines like GPUs, and a lot of data, a lot of time can be taken to train your models, and use those models inside a service to do various prediction tasks that can scale up with your service load. So that's a kind of summary of what I talked today. I talked about why conversational interfaces are so important and future of computing interfaces. What are the building blocks for building conversational interface experience, from the ability to define various workflows, and the ability to train natural language processing models, and ability to have your interactions utilizing the native messaging on conversational environment. And finally, I talked about how some of the latest advances in deep neural networks, from pre-trained language models like BERT, GPT-3, to some of the fine-tuning adaptation layers like long short-term memory network or transformer network, are making conversational AI a reality.